Hi, my name is Julian Ramirez, and for our senior capstone in mechanical engineering, we worked on a system to load inertial fusion energy targetry. Inertial fusion energy is a really promising way to generate energy through fusion. Following breakthrough ignition in 2022 at the NIF facility, there's now a huge push, a renewed interest in trying to actually scale this concept for commercial use. How does it work? Well, basically you have a tiny capsule of fusionable fuel filled with these isotopes of hydrogen and helium, and you shoot it with all these lasers in the symmetric way, spherically symmetric way, until the material inside implodes, and that process crushes the atoms together and produces energy. So pretty cool, very high tech. And so in order to actually scale this up, though, to commercial energy production levels, it's estimated that this kind of reaction, this implosion of this tiny little fusion capsule needs to happen at about 10 times a second or more. So that's a pretty lofty goal, and so a lot of smart people are working on trying to make that a reality. In our case, we're focusing on how can we actually address that problem, because right now a lot of inertial fusion experiments are not operating at the same, at a what's called reactor relevant rate. So at a rate that is close to that 10 times per second milestone. In fact, a lot of experiments take hours to set up to just implode one target at a time. So as experiments move more towards these reactor relevant conditions, there needs to be a more defined system to actually shoot them into a reactor to do experiments at higher speeds or higher frequencies.
My name is Ryan, and as my friend explained a little background of the fusion energy system, what we did is we automated the system. So we take bulk targets and pour it into this funnel, and then from the funnel it flows into the gate system, and from the gate system it ejects into these slots where they are fueled and inspected, and after one rotation they are scooped out by this impeller into the next stages. So what the next stages would be is that they would go into a sabot carriage, which is like a bullet shell, and then from there they would go into the linear inductor, and then they would be shot out onto high-powered laser, and that's where the fusion reaction happens. And this will all be in vacuum environment. And my friend here can go into details about the gate system and the rotary system.
My name is Ravi, and I'm part of the GA Autoloader team. Here we've got a gating system where basically it is a ramp set at a 7.5 degree angle. The reason behind that angle is that we want to be able to eject our IFE targets at one rate at a time. Right now it's set at 0.25 hertz. And to eject that, we use a solenoid, a 12 VDC solenoid more specifically. And that solenoid can push the targets out at about 0.4 newtons of force. We did a little ANSYS simulation here, and we saw that the IFE targets can withstand at about 4 newtons of force. So that solenoid is well within our range of specification. And then it can also be rated at a faster speed according to the angular rotation of our rotary disc. So thank you, and then I'll hand it over to Tanmay.
Hi everyone, I'm Tanmay Prakash. I'm part of the GA Autoloader team, and I'm going to be covering a major component of our design, which is the fueling stage. So if you look over here, my colleague covered a gate system that we have over here that times these targets into the fueling stage. Essentially what happens is these targets fall into these grooves, and these grooves rotate, which gives GA enough time to fuel and inspect these targets within this rotation. Now, a lot of you might be wondering, why is this circular? It's circular because we had a space constraint, and we also have a specific operational rate which we need to achieve, which is essentially we need to eject one target every 4 seconds. So what happens is this just rotates as the targets are in it. GA fuels them inside the grooves, inspects them at a separate point, and then if you see over here, there's a little impeller that essentially removes these targets out of the system. Now, these grooves are also shaped in a really interesting way. They're an Archimedean spiral. And the reason for this is we had a requirement in our project, which is essentially having a continuous system. And we ensured that using this mathematical principle that allows us to run the impeller and the disk independently. Now, the entire system is essentially actuated by 2 stepper motors, and we have a little control box that essentially ensures that these motors are specifically timed to each other, which ensures effective target, which essentially ensures that we take out the targets effectively.
Hi, I'm Colby Hettinger, and yeah, so finally our project needs to be under cryogenic and vacuum conditions. So it needs to be in a room that's about 20 Kelvin, so very cold, so that it can be fueled with liquid hydrogen. Now, a big design choice we made to accommodate for that was using a lot of aluminum. Aluminum is one of the best materials to accommodate for cryo and vacuum conditions. And yeah, later on, General Atomics is going to utilize our design and iterate forward with this. And yeah, this could be part of fusion in the future. Probably not like this exact thing, but a much more complex and iterated design. So yeah.